In the last couple of lab activities, we looked into the properties of the reactive metals and the transition metals. In this lab activity, we're going to go beyond the metals section of the periodic table, across the metalloids line, and take a look at some of the properties of nonmetals, specifically the fairly reactive nonmetals. In this lesson, we're going to be observing the element sulfur and how it behaves characteristically of the fairly reactive nonmetals. First off, let's take a look at where these elements are on the periodic table, and then let's take a look at what the properties of these elements are in order to get a good idea why sulfur behaves the way that it does. Here are the fairly reactive nonmetals, and I'm just going to pull sulfur out of the periodic table so we can look at it more closely. What you may notice, if you count the outer electrons in sulfur, there are between 4 and 6 electrons in the outer shell for these nonmetals, and sulfur has 6 electrons far away from the nucleus. Let's take a look at what this atom looks like without those 6 electrons that are far away. And then let's replace this inner core of protons, neutrons, and electrons with just a solid sphere to help us visualize. This solid sphere has to have a 6+ charge because we removed those 6 outer electrons. And now let's put those 6 outer electrons back to make this electrically neutral. This is a model of what a sulfur atom looks like. There's a few things you may think about as you look at this. First off, in order for this to have 8 electrons in its outer shell, which is the octet rule, it wants 8 in its outer shell. If it wanted to do that by forming an ion, it would have to gain 2 electrons. We already talked about how that's difficult. It's difficult for any atom to gain or lose more than 1 electron. So as a nonmetal, sulfur is going to meet the requirement of stability by getting 8 electrons in its outer shell, not by gaining or losing electrons, but by sharing pairs. And you'll notice it can share a pair on either side with other sulfur atoms. But if you keep sharing pairs on either side, you're always going to have 1 loose electron at either end, and that's not going to give you a perfectly stable arrangement. So here's how sulfur actually forms molecules in the real world. The chain of sulfur atoms doesn't just keep going on and on and on with an extra electron at the end. Those extra electrons at the end join up with each other and makes a sulfur ring. Typically, most often in nature, the sulfur ring has 8 atoms in it. So sulfur is a fairly reactive nonmetal, and it has the characteristics that the fairly reactive nonmetals typically have. Because of the way it bonds together with other sulfur atoms, it tends to keep its electrons focused in the bonds between the atoms in each molecule. Remember, metals had a sea of electrons that were just freely shared between atoms. Sulfur has tightly bonded covalent pairs of electrons that can't really move around a whole lot. However, they are able to move around just a bit. They're able to sort of randomly nudge themselves to one side of the atom, sometimes causing there to be a temporary positive charge on one side and negative charge on the other. It will induce the same charges on nearby sulfur molecules, and they will weakly bond together as a crystal. Weakly bonded like this, they have a low density. They're not really strongly attracted together like some of the metals were, which were so strongly attracted together, their density became enormous. The fairly reactive nonmetals are going to form these weak, easy to break bonds that don't really pull the molecules together very hard at all. That also gives it a low melting point because adding a little heat makes it really easy to break these bonds apart. And if you pound it with a hammer, the electrons can't just rearrange themselves like they could in the sea of electrons. These will shatter into a powder. They are brittle. And finally, the other thing that's a characteristic of the fairly reactive nonmetals is that they are able to bond in different ways to make different types of substances, even though they're made up of the same elements. We call those substances allotropes. Sulfur is able to form allotropes, and the way to do this is to take sulfur that's in its ring form and heat it up to make it a liquid, which actually adds enough energy to break the rings apart so the sulfur atoms all spread out in these long lines. And then as you let it cool down, take it off the flame, instead of cooling it down slowly and letting those rings reform, you cool it down very quickly by pouring it into cold water. And those rings do not have time to reform. Instead, what happens is the rings stay spread out in these long lines called polymers. Sulfur is actually able to make a polymer element. And when it does that, the long lines of sulfur atoms get twisted around each other. It makes a very plasticky, flexible type of substance. It's actually called plastic sulfur. So the last characteristic of the fairly reactive nonmetals is that they're able to bond in different ways. Even though they're made up of the same atoms, they form substances with different properties, and those are called allotropes. Let's take a look at what happens when we form an allotrope of sulfur. So at this point, I've got a flame going, and I'm going to melt some sulfur to take a look at its different arrangements of atoms, its allotropes. Here, I have yellow sulfur. It's a yellow powder substance comprised mainly of those 8 atom sulfur rings. In order to break those rings apart, I'm going to have to add some additional energy to the rings. And I'm going to do that over this low temperature fire. So here I'm adding energy to the sulfur, and we're going to see what happens to it as I add energy. Is it indeed going to change to a different allotrope of sulfur? Are its properties going to change even though it's made up of the same atoms? You can see already that there's a dramatic color change at the bottom of the sulfur. As I add energy to it and change the arrangement of the atoms, it goes from a yellowish color to a deep red color. As I continue heating the sulfur, you'll see that it changes to this reddish-black liquid that is still sulfur molecules, except now they're not arranged in a neat, orderly, well-packed crystal. I've raised the temperature of these sulfur rings past their melting point. However, this is still comprised mainly of those 8 atom rings. I need to continue heating it further to change it to an entirely different allotrope. As I continue to gently heat the sulfur liquid, I'm adding more and more energy to it. As I do this, the rings are going to start to break open, and it's going to change to a completely different allotrope of sulfur, a different arrangement of the atoms. Now you can see that the sulfur has formed this extremely viscous black substance. It's not very pourable. It stays pretty much in the same shape that it is in the container. We now have another allotrope of sulfur, and in order to use this, I have to continue to heat it past its melting point. I've adjusted my burner to add more oxygen to the flame to make it a much hotter flame. Now I'm going to take this new allotrope of sulfur and I'm going to heat it up to its melting point to change it from this extremely viscous liquid into one that will pour. After that, I can pour it into a beaker of water that I have to immediately cool it off. It's just started to boil. Now I've got it hot enough that it will allow me to pour it. And I'm going to pour it into a beaker of water. And here I have my final product. This is sulfur that has now been plasticized so that it's stretchy and bendy, almost like chewing gum. The reason it's the way that it is because I've added so much energy that I broke the sulfur rings apart to make long chains of sulfur, and now those chains have bonded together. Here I have an allotrope of sulfur known as plastic sulfur.